Welcome to Google Cloud's digital conference, Let's Talk AI. I'm Nithya Chandrasekaran, Strategic Partner Manager at Google Cloud.
And I'm Preston Holmes, Head of IoT Solutions at Google Cloud.
Preston and I are going to talk about Google Cloud's IoT offerings at the edge and about Google's approach to building an integrated AI platform today. We have Googlers on standby to answer your questions live, so please click on the icon to your left and ask away. The terms IoT and edge computing have been discussed a fair bit these days. IoT has grown from a concept to an exponentially fast-growing ecosystem in just a few years. To start with the basics, let's review some definitions. IoT, or Internet of Things, is essentially three interacting units in the path of connection. The first is a network of physical objects, devices, sensors, appliances, cars, etc., that connect in a wired or wireless manner to a network and have the ability to transmit data. The second is gateways, which act as bridges between the sensors and the cloud. And lastly, the cloud itself, which is used to ingest, store, process, and derive intelligence.
So it's pretty amazing the growth in the installed base and the number of devices. Some are estimating now as many as 11 billion IoT devices worldwide are already connected. And according to Gartner, this number is set to double over the next couple years, surpassing 20 billion by the year 2020.
And these devices are already generating an enormous amount of data. And to help ingest and analyze these, Google announced Cloud IoT Core last year. Cloud IoT Core is a fully managed service that allows you to easily and securely connect, manage, and ingest data from millions of globally dispersed devices. Cloud IoT Core, in combination with other services on Google Cloud IoT platform, provides a complete solution for collecting, processing, analyzing, and visualizing IoT data in real time to support improved operational efficiency.
Now, Cloud IoT Core is a great example of bringing our focus on four critical areas. First is to bring intelligence everywhere. That is to bring Google's expertise in machine learning both to operations that happen on the cloud and on the edge. The second is to bring these services in a fully serverless capacity. So we do not want people to have to manage new servers to bring this kind of capability to their applications. The third is security. So we want to take Google's approach to security design to the entire end-to-end IoT solution, both out on the device, the way it communicates with the cloud, and to data at rest on cloud platform services. And fourth is, in IoT scenarios, we have to recognize an ecosystem of partners to extend our strengths in data and data processing with areas that involve silicon, hardware-based root of trust, and new modes of RF communication.
I find that the term IoT is becoming more and more understood, but the term edge computing is less obvious. Talk of edge computing has been on the rise since we started having all this massive amounts of data generated from IoT devices. And essentially, it means the processing of data happens somewhere outside the device and before the hyperscale cloud. But the question is, what is the edge, where is it, and why do we need it?
Now, the term edge is coming up more and more, and it's really about responding to certain design requirements people have in their solutions. So while IoT generally refers to devices directly connecting to the cloud, there are more and more reasons why people want some form of computation happening nearby to devices, but before data is actually arriving at the cloud. And to answer why this is coming up more and more, it's really important to look at the motivations for why people want to look at things like the edge. And so we want to look at a few key areas we've identified at Google that bring people to us asking about the edge and the edge platforms that we can offer. The first is latency. So while our networks are probably some of the fastest you can find, there's still no way to exceed the speed of light. And so if you need certain actions to occur faster to the places where the data is being generated, you can only maintain the lowest latency if you're operating on that data on the premises where it's being generated. The second is some of the machines that we're connecting through IoT communications protocols are actually capable of generating vast amounts of data. Data that can be very expensive to transmit or may exceed the ability to transmit on the communication lines you have available at all. The third is privacy. There is going to be certain data that cannot leave the facility or the boundary in which it is generated. And while we're increasing the number of regional and geopolitical footprints where cloud services are available, there's still going to be situations in IoT where the data cannot leave the building or the room. So by bringing edge computing to that data, the immediate vicinity, it allows greater privacy preservation. So certain services that need to operate on the edge need to be reliable and operate regardless of whether the current connection to the cloud is up or down. And so that intermittent connectivity applies to IoT devices, but can apply specifically when decisions need to be made on that data on the edge. There is, again, related to this volume of data, often reasons why you need to pre-process some amount of the data locally and only send the most meaningful data for long-term storage in the cloud. Now, all of these motivations for edge apply to many different use cases, and we've listed some of them here, such as robotics or predictive maintenance of equipment, object recognition where you're using high bandwidth camera imagery, warehousing where you're trying to do route optimizations in a warehouse, or things like smart vehicles, smart cars, and self-driving cars. All of these use cases require one or more of these motivating reasons to do computing at the edge. So back in July, we announced two components that we think can help people with addressing these challenges. The first is Cloud IoT Edge, which is a software stack meant to help people run these types of edge computing workloads. And the second is a piece of hardware, which is a machine learning accelerator called Edge TPU. So things we wanted to bring in the Cloud IoT Edge offering. First of all is to bring our expertise of machine learning inference out to the edge, and that includes both software and hardware. Bring support for a new class of TPU accelerator. So while we've announced in the past TPUs as a new type of silicon that we make available in cloud data centers, Edge TPU now brings a form factor that is more appropriate for edge computing in devices. We wanted to enable a vaster type of general purpose computing at the edge. This will run on both Android things and Linux-based operating systems. And then to essentially incorporate our best practices around security and use our hardware's partners' hardware-based source of root of trust for device identity. And finally, that same best practices as far as communicating securely with Cloud IoT Core on the edge. And again, bringing back the tenet of serverless management, where in the end you don't have to deploy any new servers in the cloud to manage these new resources.
There are two key components of Cloud IoT Edge that allows you to run real-time analytics and AI at the edge. First, the TensorFlow Lite-based Edge ML runtime that performs local ML inference using pre-trained models, significantly reducing latency and increasing the versatility of edge devices. Because the Edge ML runtime interfaces with TensorFlow Lite, it can execute ML inference on a CPU, GPU, or an Edge TPU, in a gateway class device, or in an end device such as a camera. And second, the Edge IoT Core runtime that more securely connects edge devices to the cloud, enabling software and firmware updates and managing the exchange of data with Cloud IoT Core. Both of these run on the edge device running either Android Things or Linux with an optional hardware ML accelerator attached.
Now, the Cloud IoT Edge needs to not only deliver this kind of capability when running on the edge, but really to deliver the full value of edge, we need to integrate it with new cloud-based services. And the idea here is that we want to take data gathered from devices, bring that to the cloud, use it to aggregate and then train new machine learning models on the cloud, which are then delivered back down to the edge for running the inference. It's this integration between the edge and the cloud that really brings the full value of the edge runtime to the applications where it's most needed. So this brings up the Edge TPU. Now, we talked about latency as being a critical factor as one of the motivating influences of why we need to run on the edge. And while you can run machine learning models on the edge without TPU, there are a number or subset of these use cases that are particularly latency sensitive. So these are cases where you need to act in sub-second timeframes, or you may need to process multiple machine learning models in a graph or a chain. And that's why we wanted to bring Edge TPU hardware to this problem. So why did we go out and kind of build and bring out to the world this new edge TPU piece of hardware? The first is that we really recognize there's a big distinction as you bring high quality machine learning models to their use cases. So the difference in the applicability of machine learning as you go from 60% accuracy to 80, 90% accuracy is really great. And that brings with it a sort of much greater increase in the requirements for processing power. Second is we wanted to build an end-to-end AI infrastructure. So that means bringing toolkits we have on the cloud, toolkits we have in open source, and the new hardware all together into a complete package. Third is that as the advancements are happening in the machine learning algorithms, we wanted to be able to advance our silicon designs in concert with that advancement. And fourth, these are essentially now the new platform for innovation, these new combinations of algorithm and hardware co-developed together. And so we believe this is going to be a new sort of frontier of innovation and platform going forward. So I mentioned high quality. So let's talk a little bit about why this matters and why the edge TPU is so specifically relevant for high quality models. If we look at a type of image recognition scenario, in this case we're looking at a MobileNet model that we've published some research about. This typically begins with downsampling the image to a smaller image size that can be run through the model. So in this case we're looking specifically at the 224 by 224 resolution. Now, as you increase the number of million of multiply operations in the computation of running the inference, you can see that to get up to about 60% accuracy, you want to run about 120 million operations. If you want to improve that model to the point where you're getting 75% accuracy, so to go from 60% to 75%, you actually increase the number of operations to 1.2 billion operations. So that's a tenfold increase to get only 15% improvement in the accuracy. And when you look at the business use cases of machine learning at the edge, the difference between 60% accurate and 75% accurate can be all of the difference in the world in terms of whether or not it will be viable to actually deploy ML at the edge. So by bringing the acceleration and the ability to do more operations per second on hardware, we can bring a more accurate model into an effective inference time frame on the edge. And when we look at the toolkits essentially involved in building ML solutions, we recognize sort of three common stacks, whether you're talking about the edge or the cloud. And the first is really what is the hardware that this is running on? So whether this is just standard general purpose CPU, whether you're accelerating the model with graphics processing units or GPUs, or if you're using Google's proprietary and innovative tensor processing units or TPUs, this is where the actual instructions are run at the hardware level. The second layer is the hardware. So many of you have likely, if you're attending this conference, are familiar with TensorFlow. So TensorFlow is our open source framework for building and designing the neural networks and the graph models that actually compute the inference themselves. So this is where we're running that. What we're introducing as well is this neural network API on Android things that helps abstract away a bit of the hardware runtime itself. And bridging the cloud and the edge side of the software is where IoT Edge comes into play, and Edge ML. And then finally, at the AI layer, this is where we have models that we're going to be offering that are specifically pre-trained by Google and available to run on the edge, as well as software like AutoML and other ML engine cloud software development kits allow you to build and train custom models for your own use. And just to highlight here, this is the new piece that we announced this past summer around the edge TPU. So why the software and hardware are both being developed together is important is because it's often underappreciated how hard it is to get these two pieces of the overall stack to really work well together. That is, the people and the experts who are typically involved in hardware design often are not very familiar with about the specific software design approach of these new algorithms that are going to be running on that hardware. And so it's very difficult for a removed hardware team to really build the right hardware to run optimized AI algorithms if they're not also essentially sitting in the same team as the same folks who are building the software. And so we see this combination of hardware and software together as really key to the integration of the way we want to innovate on both platforms at the same time, both the hardware and the software. And that's because the algorithms that we tend to package and make available inside TensorFlow are sort of the new technology frontier. So if you look at this graph, it's showing the number of articles that have been published that are related to machine learning in one of the widely known open source journals. And you can see by the increasing slope of the curve, the rate of change in this space is very high. And so we need to be able to come up with a hardware platform that can co-evolve with that advancement. And if you look at the idea of Moore's law, the idea is that we're going to see a more rapid pace of innovation and these technology and software stacks in machine learning than we will be able to keep up with simple, sort of general purpose CPU cycles. So we really need to be able to develop dedicated hardware that can keep pace with these ML algorithms. So let's talk a little bit more about what we wanted to put into the hardware element that is the edge TPU. So this is first and foremost an inference accelerator. There will be later iterations that allow some acceleration of training, but in its first iteration we're focused on just really accelerating the performance of the inference itself, so after training. The first model of this is also developed for image applications. So we've focused on very high bandwidth buses into the edge TPU to allow high density and high resolution data to go into the edge TPU for inference. And it's also something that isn't often realized is that in a given workload or use case, it might be that you're actually running multiple models concurrently, each with their own specific aspect of contribution to the overall solution set. And these multiple models might be run in a graph. So even if you're thinking about video running at 30 frames per second, there might be multiple ML models that are applied to each frame of video. And so you may need to run 20 or 30 models within a single frame of video, and that's something that the edge TPU can enable. The other is that we need to be able to do this in devices and in scenarios where the design constraints of the case or the device itself cannot support something that's going to be pulling down, kilowatts of energy. So we're looking at this for a design target of giving you the most ML performance in the watt and cost footprint for the actual hardware. So this is targeted at something that can be deployed widely in many types of devices and not simply just a high-cost, high-power server class of hardware. And we hope that's going to really broaden the number of places that this kind of hardware accelerator can be used. So the idea is that we want to help you with the complete and integrated stack utilize this new hardware by bringing you the full integrated tool set that lets you go from idea to prototype to production. So you should be able to take a question or a business problem you have that you think machine learning might apply to, be able to quickly prove out the validity of a model, train one up, see if you can get it reasonably accurate for the first pilots, figure out how to using edge IoT and edge ML to quickly deploy that out to a device and test it in the field in an early stage, and then use that same software stack to be able to deploy it at scale in production in a fully managed way without having to retool or change how you're going about that. So let's talk about the first form factors we're going to be releasing of edge TPU. There's two that will come out in the beginning. The first is the development platform and prototyping kit. This is consisting of both a system-on module as well as a baseboard that breaks out the I/O. And the second, coming a little bit later, will be the USB-based accelerator. So on the left, when you see this development kit, there's actually two components. One is a system-on module, which is incorporating the edge TPU, a general-purpose compute processor, as well as a hardware-based secure element. This module then plugs into a baseboard, which breaks out all of the I/O pins available so that you can do prototyping on the baseboard and validate your use cases immediately. Then the module is able to be plugged into your own custom PCB later without needing to redesign that core computing element. The second component here on the right, the Edge TPU accelerator, will provide a USB-C interface for situations where you already have the compute platform established and you simply want to add only the Edge TPU hardware element itself. So Nitya, this is just the beginning, I think.
Indeed. We're at the very early stages of our journey, and we're working towards a number of goals like improving AI support, improving performance and power, adding more functionality, and we've been working with a few customers already in the very early stages, and the response has generally been very positive. IoT and edge computing are particularly relevant for sectors like smart manufacturing, real-time asset tracking, supply chain management, retail. From early detection of anomalies in manufacturing to hyper-personalized product recommendations in a retail store to collision avoidance in smart vehicles, there are a number of industrial use cases for edge computing, and the list is only growing. Our early customers, including LG CNS, for example, have used our Cloud ML engine, IoT Edge, and Edge TPU on some of their cameras to detect defects in their assembly line real-time and used it to increase their productivity. Smart parking is another early customer. They've also revolutionized the parking experience in a similar manner, utilizing Cloud IoT Edge and Edge TPUs. Of course, a partner ecosystem is very important for getting the scale needed within a short time frame. Google is aiming to provide end-to-end solutions to customers, and for this vision to be realized, we need strong partnerships. We do have a number of partners already in our ecosystem that we're working with. For example, semiconductor companies like ARM and NXP are working with us to develop the first system-on-module using Edge TPUs, which can then be used by other device makers. We also have gateway and device partners like AD-Link, Hitachi, Olia, Trax, Nokia, Kelvin, who are evaluating our platform to take Edge TPU SOM into their gateway and for incorporating Edge TPUs directly into end devices so that they can push intelligence to the edge and offer it to their customers. We are very excited by the potential of such partnerships and will be continuing to work with many more partners in the coming months.
And so if we want to zoom out and just look again one more time at where the edge sits in the context of an overall end-to-end IoT solution, we have devices on the far left. These are the things that are actually seeing or touching the world in a physical way. We then have edge computing on an edge device. This is where we're running certain types of required workloads closer to those devices, doing either machine learning inferences close to the edge or general purpose workloads. This can optionally be accelerated by our new hardware Edge TPU, and this all then communicates back to the cloud through IoT Core. So IoT Core is the gateway into all of Google Cloud Platform's complete selection of data products and storage products, where IoT data can be stored, analyzed in the long term, and combined with other business data.
Please visit these links to learn more about Google's IoT offerings, and particularly the second link, cloud.google.com/IoT-Edge, for early access to Cloud IoT Edge. Thank you for joining us today. Please stay tuned for the next session. We hope you enjoy the conference.